I want you to take a second and just imagine an environment that is actually far more hostile than outer space.
Okay.
Like, picture a domain where the darkness is absolute. The temperatures are hovering just above freezing, and the physical forces at play are so incomprehensibly massive that human survival relies entirely on the absolute, like, uncompromising perfection of engineering.
That's a terrifying thought,
Well,
honestly.
right, we're talking about a place where the margin for error isn't just small, it is mathematically zero. So you have to ask yourself, what happens when you are operating in that environment and the engineered systems you are trusting with your life experience a fundamental breakdown?
It is a sobering premise, to say the least,
Yeah.
because in our day-to-day lives, we are insulated by buffers. We don't even realize it.
Yeah,
We
exactly.
have crumple zones in our vehicles. We have redundant backup generators for critical power grids, software fail-safes, physics on the surface of the Earth that allows for those safety nets. It's forgiving.
Usually, yeah.
But down in the abyssal zone of the ocean, those terrestrial safety nets simply cannot exist. When the margin for error is zero, any deviation from structural perfection is instantly catastrophic.
And that brings us to the specific subject of today's conversation. We are examining the Ocean Gate Titan disaster. But, and this is important, we have a very precise mission for this discussion.
Right, we're narrowing the focus.
Exactly. We're going to look at this event strictly through the lens of an engineering breakdown. We're stripping away all the media circus.
All the external narratives.
Yeah, the rescue operations, the drama, we're leaving that aside to focus solely on the mechanics, the material science, and the physics of what actually happened.
Setting the parameters for this conversation is crucial because we need to unpack the core concepts surrounding this event. We need to clearly define what a submersible actually is, from a purely mechanical standpoint, especially compared to other marine vessels.
It's a completely different beast.
Completely. And we need to break down the anatomy of an engineering breakdown in the context of advanced composites and deep sea pressures. And finally, we'll analyze how the intersection of an extreme environment and a compromised engineered system just culminates in a disaster.
So let's get right into the first major concept, the submersible environment itself. Because to understand the failure of the Titan, we have to intimately understand the arena it was built to operate within.
You have to know what it was fighting against.
Exactly. The term submersible carries massive engineering implications that separate it entirely from, say, a standard submarine. I think people use those words interchangeably, but they really shouldn't.
No, the distinction between a submarine and a deep ocean submersible is vast. I mean, a standard military submarine, even a highly advanced nuclear-powered one, generally operates in the upper layers of the ocean.
We're talking relatively shallow.
Right? Depths of perhaps 1,000 to 2,000 feet, though obviously the exact numbers for military vessels are classified. But there are incredible feats of engineering. They use massive steel hulls like HY-80 or HY-100 high-yield steel to resist pressure.
But the Titanic wreckage.
Exactly. A submersible designed to reach the Titanic wreckage is diving to 12,500 feet. That is roughly 3,800 meters.
Which is just wild to wrap your head around. To put that depth into perspective for you listening, the engineering challenges at 12,500 feet represent a totally different paradigm. Let's look at the inverted spacecraft analogy.
Well, that's a great way to frame it.
Right, but let's elevate it beyond just the basics. When we think of spacecraft, we think of the vacuum of space. A spacecraft hull has to keep 1 atmosphere of pressure, which is roughly 14.7 pounds per square inch, contained inside the cabin so the astronauts can breathe.
So the pressure is pushing outward.
Exactly. The hull is essentially acting as a pressure vessel in tension. It wants to expand, like a balloon inflating.
And the structural demands for tension are something we understand very, very well in aerospace engineering. Materials like aluminum and carbon fiber perform exceptionally well under tensile stress. You pull them, and they hold.
But a deep ocean submersible is an inverted spacecraft. And the
Yeah.
forces are they're orders of magnitude higher.
It's not even a comparison, really.
It still has to maintain that internal 1 atmosphere of pressure for the crew. But outside, it isn't facing a vacuum. It is facing a crushing wall of water. At 12,500 feet, the pressure is roughly 380 atmospheres.
Let that sink in. 380 times the pressure we feel at sea level.
That translates to about 5,500 pounds of pressure pressing inward on every single square inch of the hull. Every square inch.
I always tell people, imagine a heavy-duty pickup truck resting its entire weight on a 1-inch square postage stamp.
That's insane.
And then imagine that postage stamp is covering the entire surface of the vehicle. And this isn't a localized pressure either.
Right, it's not like someone is just poking it really hard in one spot.
No, it is hydrostatic pressure, which means it is applied equally, omnidirectionally, across every single millimeter of the vessel's exterior, top, bottom, sides, everywhere all at once.
Which fundamentally changes the material science required to survive it. You are no longer designing for tensile strength where you're trying to stop something from tearing apart.
Right.
You are designing almost entirely for compressive strength. You need a structure that resists buckling, collapsing, or deforming under this relentless uniform squeeze. And historically, the answer to this has been pretty straightforward, right?
Historically, yes. The answer has always been geometric perfection, combined with materials that have incredibly high compressive yield strengths. We're talking about specialized titanium alloys or that HY100 steel we mentioned earlier.
So let's talk about that geometric perfection, because for decades, the gold standard for deep submergence vehicles has been the sphere.
The absolute gold standard.
Vehicles like the Alvin or the limiting factor, which actually went to the bottom of the Mariana Trench, even deeper, they utilize a spherical pressure hull.
And there's a very simple physical reason for that. The sphere is nature's most efficient shape for handling external pressure. Period.
Because of how it distributes the load.
Exactly. In a perfect sphere, hydrostatic pressure is distributed entirely as compressive stress throughout the material. There are no corners. There are no flat surfaces. There are no abrupt changes in geometry to create stress concentrations.
So every part of the sphere is doing the exact same amount of work to hold the water back.
The force is perfectly shared by the entire structure. It is geometrically harmonious with the environment.
But, and this is the crucial pivot here, the OceanGate Titan deviated from that geometry.
It did, significantly.
It wasn't a sphere, it was a cylinder with hemispherical titanium end bells on each side. And they chose a cylinder for a very specific practical reason. A sphere limits your internal volume.
Very much so.
A sphere large enough to hold 5 people is incredibly heavy. It's massive. It requires a specialized mothership to launch and recover. Whereas a cylinder allows you to fit more people into a more streamlined, lighter package that you can launch from a smaller platform.
Right, but the trade-off for that increased internal volume is a massive increase in structural complexity and risk.
How so?
Because a cylinder under external pressure is inherently prone to buckling. A sphere wants to shrink uniformly, but a cylinder wants to bow inward at its weakest points. And more importantly, you introduce a massive engineering challenge at the points where the cylindrical hull meets the hemispherical end bells.
Those joining points.
The interfaces, yes. Because at those points, the distribution of stress is no longer uniform. You have created an intersection where shear forces and bending moments begin to act on the materials. It's no longer just simple compression. The forces get complicated.
This perfectly illustrates the confrontation between human engineering and nature. I mean, the ocean doesn't have malice, right? It's not actively trying to crush you out of anger.
No, it's completely indifferent.
But it has absolute mathematical consistency. It applies that 5,500 pounds per square inch flawlessly and constantly. The moment the Titan entered the water, Nachi began testing the geometry and the material science of that cylinder.
Searching for a flaw.
Exactly. And that testing brings us to the second core concept of our discussion today, the anatomy of an engineering breakdown. We need to define what this actually means in a zero-tolerance environment, because it goes far beyond, like, an operator error or an unpredictable act of nature.
Right. We need to be clear on terminology. An unpredictable act of nature would be a seismic event suddenly altering the underwater topography, or a sudden, massive ocean current throwing a vessel into a rock wall.
Something completely outside the parameters of the design.
Exactly. But an engineering breakdown is a failure of the design philosophy itself. It means the materials, the geometry, or the integration of the systems fundamentally failed to withstand the environment they were expressly calculated to survive.
To really understand this, we should look at the concept of systemic integration and failure, because it's rarely just one isolated thing.
It's a cascade.
So let's take the chain link analogy, which people use all the time, but let's apply it directly to the material science of the Titan. Often, people visualize a chain as a series of heavy steel loops where one weak loop breaks and the piano falls.
The weakest link?
Right. But in the context of the Titan's experimental 5-inch thick carbon fiber hull, the chain is microscopic.
It is incredibly microscopic.
So let's break down that carbon fiber hull. Carbon fiber reinforced polymer, or CFRP. It is an incredible material. It's used heavily in aerospace, Formula One cars, high-end bicycles because it has a phenomenal strength-to-weight ratio.
It is a miracle material for specific applications.
But it is an anisotropic material. That is a huge word. Can you break down what anisotropic actually means for us?
Absolutely. Anisotropic means its physical properties are highly directional. It is not uniformly strong in all directions. It is incredibly strong when you pull on it in tension along the axis of the carbon fibers. Think of it like a rope. A rope is incredibly strong if you pull it from both ends.
Right. You could hang a car from a good rope.
But what happens if you try to push the ends of the rope together?
It just bends. It crumples instantly. It has zero compressive strength.
Exactly. Now, carbon fiber, under immense omnidirectional compression, behaves very differently than isotropic metals like titanium or steel.
And isotropic means it's uniform, right?
Yes. Metals have a uniform crystalline structure. Their properties are the same in all directions. If you push on a block of steel from the top, the side, the bottom, it resists exactly the same way. But a carbon fiber hull is a composite. It's not a single solid mass.
It's made of pieces.
It consists of miles and miles of carbon fiber thread wound tightly around a cylindrical mandrel, and it's held together by an epoxy resin matrix. It's basically baked together.
Okay, so our chain links in this scenario, going back to that analogy, are the individual carbon fibers and the epoxy holding them together.
Precisely. And when we look at an engineering breakdown in a composite material under 5500 psi of compression, we are looking at interfacial shear stress.
Interfacial shear stress, meaning the stress between the fibers and the glue.
Exactly. The epoxy matrix isn't nearly as strong as the carbon fibers themselves. Under immense pressure, microscopic defects, tiny voids, dry spots, or microscopic air bubbles trapped in the epoxy during the manufacturing process, they become focal points for stress.
So nature finds that tiny microscopic bubble of air in the glue.
And it focuses that 5,500 pounds of pressure right on it. If the epoxy matrix experiences microcracking, meaning it begins to break down on a microscopic level, it stops effectively transferring the compressive load between the carbon fibers.
The teamwork breaks down.
Yes. The load shifts unevenly. Suddenly, some fibers take on more stress than they were designed for, while others take less.
And this is where we have to discuss cyclic fatigue, which honestly might be the most insidious factor in an engineering breakdown of this type, because this wasn't the Titan's first dive.
No, it had been down multiple times.
When you dive a submersible to 12,500 feet and then bring it back to the surface, you are subjecting the hull to a massive pressure cycle. You squeeze it incredibly hard, and then you relax it. Squeeze, relax.
And we know how metals react to that. Metals have well-documented fatigue curves. We can predict with a very high degree of mathematical certainty exactly how many cycles a titanium sphere can endure before the crystalline structure begins to microfracture.
It's predictable.
Very predictable.
Carbon fiber under extreme compressive cycling is a much less mapped territory, isn't it?
It is virtually unmapped for this specific application. Every dive the Titan made wasn't just a successful trip to the Titanic. It was a cycle that potentially accumulated microscopic, undetectable damage.
Like bending a paperclip back and forth. You bend it once, it's fine. Bend it twice, it's fine. But eventually...
Eventually, it snaps. But with carbon fiber composites, it's happening internally. The fibers might survive the first bend, the first compression, but with each dive, those microcracks in the epoxy could propagate. They grow. And eventually, the layers of carbon fiber could begin to separate from one another, a process known as delamination.
Delamination. That sounds like a profound engineering breakdown.
It is the ultimate breakdown for a composite material. Once the layers separate, they are no longer working together as a single thick wall. They become a series of very thin, weak walls. The structure loses its stiffness and becomes highly susceptible to buckling under that crushing hydrostatic pressure.
And we can't ignore the integration of dissimilar materials. Because the Titan wasn't just a carbon fiber tube, it had those titanium end bells on the front and the back.
Right. This is a textbook example of complex system integration creating vulnerabilities. Anytime you join two different materials together in an extreme environment, you are asking for trouble.
Because titanium and carbon fiber have drastically different physical properties.
Drastically. They have different bulk moduli, meaning they compress at different rates under pressure. If you apply the same 5500 psi to a piece of titanium and a piece of carbon fiber, they will shrink by different amounts.
They also have different coefficients of thermal expansion, right?
Exactly, meaning they shrink at different rates in the freezing temperatures of the deep ocean. The water down there is around 34 degrees Fahrenheit.
Barely above freezing. So as the Titan descends, the water gets colder and the pressure gets higher. The carbon fiber cylinder and the titanium end bells are physically changing size and shape at different speeds.
They're literally moving against each other,
Yeah.
and they were joined together by a specialized adhesive. Just think about the job of that adhesive.
It has to hold a shifting puzzle together.
That adhesive joint had to manage the shear forces generated by two massive, rigid structures trying to compress and shrink independently of each other.
So if that adhesive joint degrades over multiple pressure cycles, or if the shear stress between the shrinking titanium and the shrinking carbon fiber exceeds the adhesive's limits,
Water ingress or structural failure at the interface is inevitable. You either get a leak, which is deadly, or you get a structural collapse, which is also deadly.
this just perfectly highlights how an engineering breakdown is rarely one isolated bolt snapping. It's not a Hollywood movie where one rivet pops and sprays water.
No, it is a systemic culmination. It is the combination of an anisotropic material being used in a compressive environment, subjected to unpredictable cyclic fatigue, bonded to a dissimilar metal, in a geometry that inherently creates stress concentrations.
The ocean is constantly interrogating the vessel. I love that phrasing. It is searching for the tiniest flaw in that complex matrix of design choices. An engineering breakdown is the exact moment the physical reality of the environment overwhelms the theoretical calculations of the system.
It's when math meets brutal reality.
Which transitions us to the third core concept we need to explore today, the reality of the disaster itself. Because when we combine the extreme, high-pressure environment we described with the systemic engineering breakdown we just analyzed, the result is definitive.
The word disaster takes on a very specific clinical meaning at 12,500 feet below the surface.
How so? Because we use the word disaster all the time. A car crash is a disaster.
Right, but in terrestrial environments, an engineering breakdown doesn't immediately equate to a catastrophic loss of life. If an airplane loses an engine at cruising altitude, it is a massive emergency, yes, but it has aerodynamics and altitude on its side. The pilots have time to attempt a glide or emergency landing.
There is a window of survivability.
Exactly, you have minutes to react. But the deep ocean offers no window, zero. The concept of survivability is binary down there. You are either perfectly isolated behind your engineered pressure hull, or you're subjected to the environment. There is no in between.
The physical reality of an implosion at 380 atmospheres is honestly difficult to even conceptualize. When a pressure vessel fails at that depth, it is not a slow leak like in a submarine movie.
No, you don't get dramatic music and a spraying hose while people scramble with wrenches. When the structural integrity finally yields, whether it was from carbon fiber delamination or interface failure at the titanium ring or sheer compressive buckling of the cylinder, the collapse happens in a fraction of a millisecond.
A millisecond.
Less than a millisecond. The surrounding water, which is being driven by 5,500 pounds of pressure per square inch, accelerates inward at supersonic speeds.
Supersonic. The water is moving faster than the speed of sound.
Yes, it collapses the hull so fast that the air inside the submersible doesn't even have time to escape. It is violently compressed in a matter of nanoseconds.
And when you compress air that quickly,
It generates heat, massive amounts of heat. This massive instantaneous compression causes the internal temperature to spike to thousands of degrees. It's a phenomenon similar to the diesel engine effect, where compressing a gas ignites the fuel, but this is on a massive, catastrophic scale.
it's unfathomable.
It is. The human nervous system literally cannot process nerve impulses fast enough to register the event. Pain takes roughly 100 milliseconds to travel to the brain. The implosion takes less than one. The transition from a functioning, humming submersible to a catastrophic collapse is instantaneous. They didn't even know it happened.
This binary reality, the fact that you're either completely safe or completely gone in a millisecond, brings up a really fascinating psychological component of engineering.
It's the human element.
Right. Humans rely deeply on the machines we build to conquer our primal fears of hostile environments. We have to, or we'd never leave our houses.
We operate under an illusion of safety. I want to be clear, it's a scientifically backed illusion most of the time. It's built on centuries of material science and math, but psychologically it remains a construct.
Think about it. When you step into an elevator, you don't actively worry about the tensile strength of the steel cables above you. You don't do the math on the sheer strength of the brake calipers. You just press the button and trust the engineering.
You abstract the danger away. When the passengers on the Titan looked out the viewport into the freezing abyss, the hum of the life support, the warmth of the cabin, and the physical barrier of the hull told their brains they had conquered the environment. Their brains said, "I am safe."
And the engineering of the Titan actually leaned into this psychology with its real-time acoustic monitoring system. This is a crucial point to discuss.
It is perhaps the most glaring example of a philosophical engineering breakdown in the entire system.
Explain how that system was supposed to work.
Well, the designers recognized that carbon fiber under compressive stress might fail unpredictably. They knew the material was experimental in this application, so they installed highly sensitive acoustic sensors inside the hull to listen for the sound of carbon fibers snapping.
Like microphones listening to the walls.
Basically.
Yeah.
The theory was that as the hull experienced stress, snapping fibers or cracking epoxy would create a distinct acoustic signature, a warning sound.
Warning the pilot that a failure was imminent.
Right. The idea was that if they heard popping or snapping, it meant the hull was reaching its limit. The pilot would then have time to drop the external weights and ascend back to the surface before the hull completely failed.
But relying on acoustic emissions as a primary safety mechanism for a brittle failure mode in a zero-tolerance environment, that is highly controversial in the engineering community, isn't it?
Controversial is putting it mildly. It is fundamentally flawed because it assumes that the material will give you a gradual linear warning.
It assumes you have time.
Yes, it assumes that there will be a sufficient actionable gap in time between the sound of a few fibers snapping and the catastrophic delamination and buckling of the entire hull.
Yeah.
But advanced composites don't always fail linearly. They can fail exponentially.
Non-linearly.
Exactly. You might hear a few snaps and you think, okay, we have 10 minutes to get up. But milliseconds later, the entire matrix fails. The time between the warning and the catastrophe could be a fraction of a second.
So the acoustic monitoring system provided a digital dashboard that effectively said, "You are safe. Everything is green."
Until it wasn't.
It reinforced the illusion of safety right up until the exact moment the engineering breakdown occurred. It was a safety net designed for a slow-moving terrestrial failure, like a bridge slowly groaning before it sags, applied to an environment that operates in milliseconds.
When an engineering breakdown occurs at 12,500 feet, it shatters that illusion of safety violently. It is the sudden catastrophic reassertion of nature over human ambition. The psychological contract we make with our machines is voided instantly.
The ocean environment was never really conquered by the Titan. It was only temporarily held at bay by a highly complex, highly experimental barrier. And when the weakest link in that systemic chain finally gave way, the disaster was absolute.
This synthesizes the entire scope of our discussion today. The OceanGate Titan disaster is fundamentally defined by the failure of its engineering to withstand its environment. It is a closed-loop equation.
Break down that equation for us.
You have the environment on one side, the crushing omnidirectional 380 atmospheres of hydrostatic pressure. You have the engineering breakdown in the middle, the systemic failure of composite materials, dissimilar metal interfaces, and unmapped cyclic fatigue. And you have the disaster on the other side, the immediate, unforgiving consequence of that breakdown.
So let's quickly summarize the ground we've covered today for you listening. We started by defining the sheer hostility of the abyssal zone. We moved past the basic idea of a submarine and examined the precise physics of an inverted spacecraft, where the engineering challenge is entirely about resisting immense, constant compressive force.
We then deconstructed the reality of an engineering breakdown. We moved away from the idea of simple accidents and really focused on the material science.
We analyzed how an anisotropic material like carbon fiber behaves, or rather misbehaves, under extreme compression, the dangers of microcracking in the epoxy, delamination,
And the immense complexities of bonding dissimilar materials like titanium and carbon fiber under varying thermal and pressure conditions.
We looked at the compounding danger of cyclic fatigue, recognizing that every dive was a stress test on a novel experimental structure. And finally, we discussed the unforgiving nature of the disaster itself, how the deep ocean eliminates the concept of a minor accident, turning any structural yield into an instantaneous, catastrophic implosion.
We also examined the psychological illusion of safety, specifically how systems like real-time acoustic monitoring can provide false confidence in an environment that affords zero reaction time.
Which leaves us with a critical connection back to you, the listener, because
Yeah.
the reason we analyze an event like this so clinically isn't just to look backward or gawk at a tragedy, it is to understand the future. Humans are intrinsically driven to push boundaries.
We always have been. We're going to continue exploring the deep ocean. We're going to push further into the vacuum of space and other extreme environments. It's in our nature.
And our reliance on highly complex experimental engineering is only going to increase as we push further into the unknown.
Understanding the anatomy of an engineering breakdown, understanding the absolute limits of material science, the dangers of systemic integration flaws, and the complete lack of forgiveness in extreme environments that is the only way innovation can proceed safely.
It requires rigorous, objective analysis of the systems we trust with human lives.
It demands that we recognize the inherent risks when we deviate from proven geometries and materials, and that we never, ever let the ambition of exploration blind us to the mathematical realities of physics.
Physics always wins. Which leaves a lingering question for you to consider long after this conversation ends. As we inevitably continue to build machines to take us into the most hostile environments in the universe, where exactly is the line between innovative, boundary-pushing engineering and an inevitable systemic breakdown?
It's a very fine line.
It's a complex reality to ponder the next time you find yourself relying on the engineered barriers between you and the elements. Thanks for joining us for this conversation.